So to get started, I'll introduce our first speaker today, Dr. Dan Tingley. Dan Tingley serves as Executive Director for Wood Research and Development. Dr. Tingley has worked in the wood products industry for over 40 years. He received his Bachelor of Science in Forest Engineering and Master of Science in Civil Engineering from the University of New Brunswick, and he completed his PhD at Oregon State University in Wood Science, Technology, and Civil Engineering. Dr. Tingley currently holds more than 40 published patents in the reinforced wood field in the US and other countries. He has authored over 125 conference proceedings, publications, and articles in the area of reinforcement of wood and wood composites. So Dan, we won't waste any time there. I'll pass it over to you and we can get started. Look forward to your presentation.
Thanks. Welcome, everyone, and it's good to be here with you this morning. And it's always great to be able to talk about timber. It's a topic that I'm passionate about and spent a career in, and so I always welcome an opportunity to talk about the things related to timber. And you know, it's our past, its present, and our future. And no more is this evident than it is today as we see this explosion of mass timber in the marketplace around the world today. By some estimates, by 2030, there'll be 30% of downtown cores will be mass timber as we move forward in a kind of sustainable material, carbon friendly, that has so many great attributes. And so who am I? Dave's kind of introduced me a bit. It's always nice to be on a presentation in the Maritimes. I'm talking to you this morning from Jefferson, Oregon, out in the West Coast. And I make my home now in Jacksonville, and I grew up in an area below Moncton, down by the rocks in Albert County, if anybody's familiar with it. And I started my career many years ago in the business of wood. And you can see the little dots here and the highest tides in the world. That's where I grew up. And of course, in New Brunswick, we are famous for our longest covered bridge in Heartland, New Brunswick. That's been around for a long, long time. And of course, we're, without even knowing it, we should be famous for other mass timber projects like Bell Dome up in Beldoon, a 535-foot clear span, 12-story building, and you know, for coal storage where SO2 is an issue, and potash where salt's an issue. Here you can see in Sussex and St. John, large timber buildings, which engineers and architects and owners have been understanding for a long time provides for a rigorous resistance to different types of corrosive environments. And timber has been shining through in that way for many, many years, decades. And Wood Research and Development, who I work for, we're a code certified test lab and third party, IAS, International Accreditation Service. And as well, we have a strong, large commercial timber structures and engineering division. And we work from the small to the large in our lab. We get pieces of wood and people ask us to identify the species and grade. And we look under a microscope and look at the smallest portions of a piece of Doug fir, for example, here on the right side, where you see spiral thickenings on the cell wall, a dead giveaway for Douglas fir. On through to other, you know, different types of characteristics that we look at to identify wood at its smallest and minute level. And from there, we go to the big levels, testing full-scale beams with our big beam testers, where we test reinforced glulam beams and other large timber products as part of our work, strain gauging them and measuring deformation under deflection and understanding what their characteristics are and their physical and mechanical attributes are rather to work for things like establishing design methodologies for code approvals. This often leads to understandings about shear stress distribution, for example, in beams, and high-speed video where we take a post trigger and look at the effects of stacking two finger joints in the bottom of a glulam beam and the effects of what happens when you join them with a finger joint between a very dense and a not so dense lamination. Part of what we do at the lab to understand the response mechanisms to load and solid sawn, how to fix solid sawn, for example, with high strength fiber. And part of our work at the lab has been producing and developing high strength fiber using carbon and glass and aramid, that's Kevlar, to produce in high strength fiber layers that we're able to use strategically in different wood and wood composites, where they're 5 times the strength of steel at a fifth the dead weight, and they come on a roll, and you can stretch that roll out 2,000 meters if you want, and cut it in pieces and put it where you want. All kinds of different characteristics involved, different physical attributes and mechanical properties, but these all work together well with wood. So well that we can look at a 42% reduction in wood fiber content and carrying the same load and using low-grade wood, as you can see here. This fellow on the left is equal in strength to the guy on the right. So this has led to, you know, and I don't want to brag, but it's an area that's important to know that what we talk about with wood and ways of enforcing it is bona fide. In '96, we were nominated for the Civil Engineering Research Foundation Charles Pankow Award for Structural Innovation. And then in '97, the Construction Innovation Forum Award for all construction products. We were fortunate enough to win both of those back-to-backs, first time ever won by wood in the world today. And that was the beginning, in many ways, 25 years ago, of this great move we see back to wood now in this last decade. This has led to other award-winning projects like the Nepan job, for example, near Amherst, Nova Scotia, the Roger Bacon Bridge, where we won the Merit Award last 2 years ago for that bridge. So other things, aspects, you know, this is an important aspect of protecting technologies, but again, as a Canadian, it's important for me to think about these things. You know, we were successful in over 40 patents in this whole area of wood and wood composites. So enough bragging. You know, this has taken me through a career where, from how stuff works on the Discovery Channel to being around the world looking at different wooden structures and helping people understand how to fix them, how to extend life, and understand what's going on with their structures. We have a whole range of timber structure training courses. You can see here talking about different aspects of timber, 16 different courses that give you continuing education units. For those that are interested, you can connect with David after, and we can get you into one of these courses if you're interested. And these courses provide all kinds of different ideas and concepts that are important in your career as far as designing and working with wood. As you can see, a class here in Salisbury, and a fellow from South Africa and a guy from Italy working together to develop a restoration for poles and wrapping for piles and diffusing and using naturally occurring salts to preserve the life and extend the life of species that are not treatable, like spruce. So this leads to certificates of completion, as you can see here, for people that attend. So enough of that. Timber is one of the oldest bridge building materials that's been around, and both bridges and buildings have been built out of wood forever, it seems, originating back to the 1500s. You can see 15,000 BC. Timber, the material, is readily available. Where you go, timber. In the old days, we used to build a railway across our continent, and we'd reach a gap, a river, or a big gully, and they cut down the trees that were there to make for a bridge to get across it. And this was the beginning, as it were, of the use of timber in a more capital infrastructure way, as you can see here. And timber formed up the backbone of how we build things and what we do as a material to design with it. These are the important aspects of our history with timber. And the breadbasket of the world really became the northwest part of the United States and the western part of Canada, where these huge trees were fallen. You can see one tree, one train, and it was location, location, location. It was about where was the wood, and that was what you were using, because it was local and the people could get at it and machine it and use it and design it and build structures with it. And as you can see, the size of the Doug fir here cut down, this is some big trees. And I often say, if you can't make money cutting trees like this down, you want to get out of business. Huge trees providing for a breadbasket to build the world, as it were. And so trees have, you know, timber properties. They kind of grow the same way. They get bark, they have cambium, the growth area in the church, in the log, and there's growth rings, as you can see here, and heartwood and sapwood. And this kind of breakout of a timber cross-section of a log is the same around the world. And timber properties, you hear oftentimes the old growth timber. You refer to it as old growth. These are the old Doug fir trees, for example, and redwood and western red cedar, these old trees that are large and growing at tight spacings. And you often hear people say this old growth is gone. And this means we can't have strong wood. Well, that's just not true. Younger trees, for example, convert much more CO2 to oxygen than old growth trees. And we are carbon negative through that issue. We sequester carbon. And so our old trees are good to walk through and they're good to keep for the heritage. But really the regenerating trees that we plant 2 for 1 that we can then saw down and make into things, make into composites of wood are the way forward for us, because it's sustainable. Taking these regenerated trees that are planted 2 for 1 and growing forest with them allow us to sustainably create building materials and not pump CO2 into the atmosphere, but instead convert it to oxygen and sequester the carbon and keep that carbon sequestered in structures that we build around us that are aesthetically pleasing. So we often say, good wood is gone. It's harder and harder to find, and quality wood is just not there because we have to deal with regen. Well, I want to tell you that it's far more common with wood structures that it's how we design and manufacture and work with this that causes the premature failures than it is the wood. It comes from a lack of understanding. I often show this picture of the petrified forest in the national park in Arizona, where dug fir trees are laying in the ash that have been uncovered from the winds of time. And they kind of got together in the great inland ocean. When the ocean receded, they settled and they mineralized and formed into agates, basically become petrified. And they've studied these petrified chunks of log and found out that this dug fir trees were growing 250 million years ago, the same way they're growing today. And those trees have not changed in how they grow. They basically have the timber properties that originate from how they grow, cambium and growth rings, for example, and rays and early wood and late wood. These cellular structures, what forms up timber. And timber has 3 principal directions of strength. It's anisotropic. It means that it has different properties in different directions. It's got a radial direction, a tangential direction, and a longitudinal direction. And in the radial direction, the modulus of elasticity and tension is different than the modulus of elasticity and tension in the tangential direction. And if you try to design timber like you design steel, you're going to make some serious mistakes. And on top of its anisotropic nature, wood also is hygroscopic. It breathes in and out moisture. After all, it was a living organism in its origin, and it breathes in and out moisture and equivalates with its surroundings. And so those 2 big factors are important to consider when we consider designing with it. It's a collection of cells bound together by lignin, the glue. And this collection of cells has properties that are related to its orientation and how the cells and lignin formed it up. Timber's properties, for example, between hardwoods on the left and softwoods on the right, the softwoods are geotropic, and they grow in response to gravity, straight up and down, so they tend to have less slope of grain issues. Hardwood trees on the left are phototropic. They reach for the light. They tend to have more slope of grain issues, even though they're denser and more complex. And so these aspects of timber are important for engineers to understand as we design with it. And this anisotropic slope of grain and strength issues that are relating to how we cut pieces of timber out of the log are also important, because slope of grain relates to cutting a straight piece of lumber out of a tapered or round bolt or log. So in addition to that, as I talked about, timber being hygroscopic means that it breathes in and out water, as I said, and there's a point where it's giving off water, cell water, what we call free water, lumen water, that it doesn't shrink with change in moisture. And when we get down to cell water, that's the bound water, what's in those cell walls. When it loses moisture from that point, it shrinks. And that FSP, we call it, fiber saturation point, is around 25 to 30% moisture by weight. And when wood drops below that, then it begins to shrink. And when it moves in and out of moisture below that amount, it shrinks and expands. And so we take engineered wood products like glulam beam, for example, manufactured between 12 and 15% MC. One of the key reasons they are is because it's middle between FSP and 0. that means it shrinks and expands the least amount. It's more stable. Where you take LVL or some of the other engineered wood products made at 8 to 10%, they're drier than glulam, or what we call structural kiln dried wood, which is dried to 19% or less. Different types of engineered wood and different types of salts on wood are at different moistures. And so when I hear the term wood is kiln dried, the first thing I say, kiln dried to what? And so this fiber saturation point is a critical point, because why? We have to understand that wood shrinkage longitudinally is negligible. Its shrinkage tangentially and radially is very important. It changes the game, as it were, on multiple story buildings, for example. Rays transfer moisture in and out of the radial section of the tree, and then they're kind of nature's natural fault line as the tree shrinks and expands. And there's where you see these non-structural defects forming in timber. If you don't know this is a non-structural defect and you're looking at this log in a log girder bridge system, the first thing you're saying is it's shear failed. Well, that's not shear failed. It's not shear failed at all. It's a naturally occurring shrinkage checks, because at the end grain travel of moisture is 100 times faster than side. And so that tends to lead to end checking and end feathering. And these vertical cells that take moisture up and down the tree, they kind of move along naturally. So just because the tree is cut down and is sawn into timber doesn't mean that moisture isn't going to move through the cells. So when you put a pile or a column in the ground and it gets groundwater, the water moves up in that tree the same way it did when it was living, by capillary action. So water moves through and in around wood a lot. And the specific gravity of wood, which is its ratio of the wood's density to the density of water, that ratio is unitless. And wood has all kinds of different specific gravities. Some wood, like ironbark, sink when you throw it in the wood. It's denser than water. Other woods, like balsa and western red, are a third the density of water. And so typically this density is kind of related to the wood's characteristics and strength, but other localized defects like knots and slope of grain will also impact that design property in the wood. So these properties related to density usually mean that the heartwood kind of more inert and the sapwood kind of more open to moisture travel and permeable. They impact the quality and condition of our elements as we use them. Typically in the day past, wood was sawn around. We'd take a big square bolt out of the center after we cut the jacket wood, it's called, into the kind of higher grade wood, because there'd be less knots out. The Boston heart timbers were used to build bridges, heavy timbers for post and beam homes, for example. So timber properties are affected by knots, splits, checks, temperature, moisture, all impact the design properties. And most of these design properties have been developed from understanding things like wane and knots and the size of knot in a section, and things like checks and seasoning issues. They're reflected in the design values that we already have published for use by engineers. So other things can affect timber, like temperature, although it's got very good resistance up to 150 F in terms of its strength. And at extremely low temperatures, if it's green, it can have it can shatter because of sudden impact, for example, in terms of the deep freeze up in the boreal forest, for example, in northern Canada, and it comes in quickly before the tree's moisture content is kind of dropped into its roots. You can hear loud reports where trees literally split because of freezing water in them. And so temperature does impact timber, but not to the extent that it would, for example, in steel. Its coefficient of thermal expansion is much, much lower than steel. A timber's properties are impacted by moisture. Generally, modulus elasticity and strength increase with a decrease in moisture content below FSP. And wood's bending properties, for example, heavily impacted by knots, slope of grain. So if you have bigger knots in a smaller cross section, you have less strength. The knot is denser than the wood around it, but it's the slope of grain around it that creates the localized defects that lead to reduced strength and capacity. Same goes with compression parallel to grain for columns. Same goes with compression perp to grain. Most people don't realize that compression perp to grain strength values are a specific criteria. They're the capacity of the piece to accept a bearing perp to grain, and it's the stress that causes 1 millimeter of deformation. It's a specific characteristic, not a strength characteristic. So bending, extreme stress, and log form. This is, design properties like horizontal shear. This is not a shear split. It's not a shear failure in horizontal. It's a shrinkage crack. And you can tell that by the piece of grain that's hanging onto the edge. This is a horizontal shear crack. 60% of all horizontal shear failures in wood occur along the late wood, early wood interface, as you can see here. That's a horizontal shear crack. That's a horizontal shear crack. That is not. That's a boxed in heart with a shallow grain at this edge. And that's a ray, and it shrinks and seasons. And as it does, the cells, which are circle around the annual ring, shrink, and they lead to nature's natural fault line, a ray, which separates at that point. That is not a structural defect. This is not a structural defect. So there's a difference between a shrinkage crack and a horizontal shear crack. This is a shrinkage check. This is a horizontal shear failure. I wish that I had been able to see a video like this when I was in my undergraduate program at University of New Brunswick, because I always thought that shear was a transverse deal because the 3 has VA. And that's horizontal shear, and it's overloaded because of heavies. And that horizontal shear is rubbing the wood back and forth. And the white is the wood powder that's coming off, and the vertical spikes from the top are leading to water flushing out that wood powder. That's a horizontal shear failure. So horizontal shear failures can be improved, by putting a horizontal shear reinforcement. As you see this big cap here for the Nepan Bridge, we put horizontal shear panel on, and that carries a huge point load. So instead of us having to increase the size of the beam everywhere, we can strategically place horizontal shear reinforcement to increase the capacity of that piece at a point load and build the bridge more economically and effectively, so that you can build timber bridges that replace steel bridges like this, because the steel isn't cutting it. It went 48 years and quit. You couldn't keep sandblasting it and priming it and painting it enough to keep it survival, because it was in the highest embedded and exposure and corrosion zone in the country. And this shear panel allows us to improve shear capacity. You can see here the hazard zones for North America, and you look at Nova Scotia where that Roger Bacon Bridge is, and this is why the Nova Scotia government doesn't like to use rust-resistant steel. It's an extremely severe zone on the East Coast for steel. It's a hard area to build. This is rust-resistant steel that's gone in 18 years. 18 years, rust-resistant steel. This is painted and primed steel that's rusted out in 42 years. And so timber has its naturally occurring resistances like this. It doesn't rust. That's why we use wood in swimming pools. That's why we use pool over saltwater pools and chlorine pools, because wood has great natural resistance to these sorts of environments, like salt for potash terminals, like SO2 for coal storage. That's why we choose wood, because it's this naturally occurring resistance that make it the right choice for things like fish hatcheries, for example, like this one, where we can produce these naturally occurring wood products that are sustainable, carbon friendly, that are going to go the distance in kind of hard environments, like a pulp and paper mill with a steam. These are all timber beams in the roof of this pulp and paper mill, because they know they do better in these environments. So timber can be quite durable. Timber does not behave in a truly elastic mode when it's under time-dependent behaviors. That's why we have in its composite adjustment factors a DOL, duration of load factor, of 1.6, because timber tends to have a viscoelastic response, and over time will creep. And if you put too much load on it, then it can creep to failure. So we adjust for that. And so when people say that timber creeps and that you can't use it as a structural material, they don't understand that we've already accommodated that in our design values and in our composite adjustment factors, and that you can have timber carry loads. And so our design standards work like this: our National Building Code, our 086, our Timber Engineering Code, and then the Highway Bridge Code, which stands between 086 and the site, our Wood Preservation Codes. These codes allow engineers to go into the marketplace and design timber for people in different uses and produce for clients a working drawing set that will allow them to go out with a contractor and do the right kind of job at building their structure. And so who stands between the designer and the design codes? Well, there's grading agencies. These grading agencies provide ways for manufacturers of products to be able to grade their materials so that they put a stamp on it that they then relates to the drawings that the engineers have used, because that stamp and grade of lumber is covered under the design standard, and the engineer uses a design standard to choose the right choices for his design. And then he puts a drawing together and puts on that drawing what grade it should be. And so I never was taught one time in my undergraduate and postgraduate training of 12 years that there was an upside down for a large dimension timber, that we put the bigger knots at the top, and when we grade them according to knot size and slope of grain. And so if you don't, and you end up putting the big knots at the bottom by just not turning them right side up, guess what happens? Premature failure of pieces and around knots, which occurred at the bottom. And this is not good. So, you know, timber bridges and buildings, like we say, have been around since the beginning of time. You know, this bridge here, 500 to 600 years, it's naturally grown. It's Viscus benjamina in India, in one of the worst environments for timber, but yet it's there for 600 years. They liked it so much, they drew a double-decker bridge, and then they grew their handrails. And why is it lasting? Because they grow their connectors, because the devil's in the details. And this bridge, 500 years in Japan, the devil's in the details. It's a leaf spring bridge, and it's going the distance because it's properly designed, proper ways for water to get off, and it's reflected in its design criteria of getting newer. This bridge, 1936, the longest suspension bridge in Australia. Proper designs keep these bridges going longer, lasting the test of time. The devil's in the details. It's not the timber can't last. It's not that it is the wrong material for choice. It's more that we don't know how to deal with it effectively and design with it. When we think of saying rot in timber is dry rot, there's no such thing as dry rot. It doesn't exist. It's an oxymoron. Google it after you're done with me. Dry and rot don't go together. If you don't have wet, you don't have rot. So dry rot is what's left after the decay-causing colony has moved on and it's kind of dried out, crumbly, and so on. There's just no such thing as dry rot. So if you're designing bridges and buildings to accommodate proper characteristics under different environments, you're going to have longevity. It's not timber's fault. It's not wood's fault. It's how it's design's fault. This is a bridge in South Dakota near Keystone Wise near Mount Rushmore. And this bridge is very old in the scope of time, not as old as hundreds and 200s and 500 years old, but still old. Constructed in 1966. It's made from Doug fir, pentachlorophenol treated, and they wanted to replace it. 23 million. They asked us to come in and take a look at it. The deck had been replaced 3 times. It was concrete. The wood was still there. And we could only find 3 bad actors in the whole bridge system. And they're fixing it now for 4.3 million. And so being able to get longevity is what bridge and building owners are looking for. Mechanisms to support decay are heat, moisture, and oxygen. If we don't have any of these 3 items, the wood is the food source, then wood doesn't decay. The spores are on everything. They're on all pieces of timber. They grow a hyphae that secretes, has a foot at the end of it and secretes an enzyme that breaks the wood down. And we don't want that natural cycle of life to occur in our products. So one of the things we do is we pre-manufacture and pre-assemble and pre-machine our bridges, for example, in a factory, and then take them all apart and post-treat them. So there's no bright wood, untreated wood. And then that bridge can have a 100-year design lifetime. And when it gets in service, it goes together much more quickly and effectively, as you can see here, producing something that's naturally aesthetically pleasing, that's going to go the distance and carry heavy truck traffic. And this bridge lasts the length of time. Instead of shipping a bundle of treated wood to the site, machining it, cutting it, and leaving all kinds of bright that then leads to decay, we short circuit that problem and do it in advance and post-treat. The early designers realized that their way of doing that was to put a roof over it. So all the covered bridges, for example, in New Brunswick, this is Milky's that I designed a restoration for. The early designers from Europe realized that if I had a Howe truss and if I put a cover over it and kept water off the joints, I could have that bridge to last a long, long time. And that's why bridges are covered, because it keeps water off the joints. And so in buildings, we do the same thing with outdoor structures. We keep water off them. We do great jobs in Vienna, the wave. You can see we keep water off it by putting a roof over it. This is in Switzerland, a beam set I designed. You can see the depth of it. We used strategic oak shoes, and we had strategic placement of high strength fiber, and allowed this building to be built at a reduced cost because we wanted to do a more effective job. You can see back here where I have hair and actually brown, and I'm doing some quality control checking on big beams. These are big, what we called in the day, post and beam glulam structures, which we would call today mass timber. These buildings have been going on for decades, since the 50s with glulam beams. And you can see this one here being built as half the length of beam, some of the biggest beams ever built, and built with low-grade blowdown wood for McDonald's. And we parked them across the Autobahn, and we installed this roof system in about 7, 8 days using this blowdown wood, McDonald's building with high winds wood. And so this is in Vienna, another design I have out where I won an architectural award for, where we had this kind of pinned rigid C shape and reinforced in a starburst of dowels, you can see here, to try and get the look we wanted and the performance we wanted. These are the old panelized roof systems that we used for decades that were supplanted by steel and bar joist in the mid to late 90s, which are now coming back again, providing for cantilevers for good mechanical advantage with drop-ins. And you can see these sorts of buildings. And these buildings, big dome buildings, as you can see here, again, kind of testimony to what we used to see Tacoma Dome in 4 decades of work. And so understanding timber and how it's changed over the last decades is pretty important, because we've come kind of full circle. At the turn of the century, 82% of the bridges were timber. Now 1% is. When I graduated in the 70s, early 70s, we were building post and beam and heavy dimension timber. And over a process of time in the bridge market, the precast concrete bridge girder system come to play, and timber was pushed out. Today, that's changing as people look at things through a carbon lens and think of things from a sustainable point of view. They think of it from a maintenance point of view, from a capital cost point of view, and timber is coming back. Well, in that 4 decades of kind of dropping off of interest in timber, universities stopped teaching. And, you know, they just stopped teaching students about timber. And so now schools are beginning to explore ways to produce additional timber education and curriculums, because there's a demand in the marketplace today. And with that demand has come new types of timber products like CLT, another mass timber product that you see for walls, floors, and roofs, combined with glulam. And mass timber is lightweight compared to steel and concrete. It's faster to install, takes smaller equipment, reduce transportation costs, reduce structural loads from dead weights. You can prefabricate the components like you see in my bridges. And these prefabricated components go together on site much more quickly. And of course, it has these great environmental advantages, to say nothing of the aesthetic advantages. And one of the key reasons over the years, even including the Europeans and ourselves, that timber has stayed in the running and is now coming back to being in the running is its dead weight. You think of the fact that a concrete precast bridge is 8 times heavier than timber, and some structures, concrete structures versus mass timber structures, are 5, 6, and 7 times heavier. This dead weight is a big factor in the design. So this CLT production, which is a part of the mass timber lineup, has really exponentially grown. As you can see here, this huge increase. And there's a rush in the marketplace to produce this new material. And this new material kind of is adding to the tool bag that engineers have had. We've had, parallel strand lumber, glulam beams, LVL, different types of engineered wood for decades. Now comes another kind of engineered wood, CLT, both in the heavy solid sawn timber lamination side and in the veneer side, as another tool for our tool bag to build these great buildings that look and feel and touch are so important to the community. Sustaining carbon by sequestering it, and having a sustainable building product, as you can see here in these buildings. A huge improvement over the way we build structures today as we look at where we're going now in this next few decades with pre-cut panels that allow us to basically form up high-rise structures. And codes and universities are racing to keep up with the marketplace as we go to 20 stories and 30 stories. And now the Arabs talking about 126-story building out of timber. So these are the ways we're moving in our industry today as we look down the path that we're on. You can see these beautiful structures. I mean, this is kind of the way forward for us. Tall, high rises, small to large in terms of structures. Beautifully, aesthetically pleasing structures that combine sustainability, carbon sequestering, aesthetically pleasing views that are healthier to be in and live in. And this is our way forward, not spewing CO2 into the atmosphere, but instead capturing it and sequestering it, as you can see here. So this is one of the bridges that in Carinthia in Austria that I designed many years ago, going into place here. It has that look and touch and feel on the Roman road. That's where you want to be when you're building bridges. And nail laminated timber is on the scene as well, producing another form of mass timber for the engineers in their tool bag. Another material, or dowel laminated timber, as you can see here, another tool for their tool bag to go with the LVL and Paralam tools that they've had, orientated strand board, plywood that have been in their lineup, and the oldest of them, of course, solid sawn timber, which has been around for a long time. The manufacturing of these new materials, however, brings with it some different design criteria and quality control criteria, which we need to reflect on. You know, dry block shear testing is a part of the quality control in the manufacturing of engineered wood. We need to assure ourselves that glue lines are doing the job. We don't want delamination because wood is hygroscopic, breathes in and out moisture, and delams or doesn't have the right glue line. And so part of this process of building these new materials is looking at things like the shear capacity between RP, reinforced polymer, and wood. And then doing another step, which is cyclic delam. That's where you put them in a vacuum pressure chamber. You fully saturate things, representing the hygroscopic nature of wood, taking it from, say, 12 to 15% moisture, past FSP up to 30, 40% moisture, and then putting it in an oven. You can see the piece in here with high strength fiber, doing tests, putting it in an oven and drying it out back to 15% of its original weight and looking for things like delam. And the wider the piece, the more potential we have for delam. And the industry sets standards of 1 cycle, we have 5% delam allowed. After 2 cycles, 10%. So if you're over that, you're failing. What's the significance? Well, if I have wood in my building and it changes in moisture content, we don't want to have the glue lines open up and it delam, because if plane sections don't remain plane, we're not going to have a composite action, and we're not going to be able to use the design values we use to design the building. So we don't want delam. And so we test in our quality control system these aspects of our beams. We look for delam, pass-in and failure. And then when we look, for example, at CLT, most of it made with polyurethane, and it's indoor use. When I say wet service, I'm meaning what happens when it cycles moisture. I don't mean whether it's going to survive in the decay-prone areas like a bridge. I mean what happens when it cycles moisture. And that moisture cycling resistance is pretty critical. And as you can see here, this is results here from CLT testing. The polyurethane glues are not really effective in moisture cycling resistance, so we have to keep them indoors and out of wet service while we tarp layers when we're raising up buildings out of mass timber. We don't want this cycling to lead to delam like this. So if we want to prevent this, we need to move to resorcinol, phenolic glues, and control the conditions of the effective width so that we don't have the extra width that leads to more tension perp to grain, which is caused by differential shrinkage, where one guy shrinks a lot more than the other guy. This guy's shrinking here, say 3% from FSP to 0. Lengthwise, this piece is shrinking next to nothing, 0.01. When you put a lot of shrinkage next to no shrinkage, it puts tension perp to grain on that glue line and peels it. And we don't want that to happen to our CLT panels, so we understand. And even two-way glulam beams can have shrinkage issues. In this particular case, the glue lines have been strong enough to cause the shrinkage to occur in ray lines and not in the glue lines, which is what we want. Some places, as you can see here at the 23 and 15, it didn't pass. So we're watching these aspects of our engineered wood products pretty closely. And it's important for engineers and specifiers and owners to also know these things so that they, in their interactions with manufacturers, suppliers, and other engineers, they're thinking about the important aspects of this side of an engineered wood. The design values for various engineered wood products, I got this big table. I know it's busy and I know I shouldn't put it on the screen, but I wanted to use this table to just show you how you look at glulam, solid sawn, CLT, microlam, paralam, LVL mass timber, LVL as it is, and you look at things like the shear values all the way down through here. All of these different products have different strength values because we've orientated wood fiber in certain directions. And there are various design values from 30 MPa all the way down to 0.1 and 0.2. And CLT has what we call a major and minor axis. That means that its strength and bending in the what we call its major axis longitudinal is different than its strength and bending in the transverse, almost triple the difference. In its shear, for example, we might have a shear value difference of 2.4, for example, of PSL to 0.4 for certain types of veneer type mass timber, some 0.1. These are huge differences. And we have to understand those differences. And a key point that I want to talk about today is panel point load testing. When we use mass timber for bridges where there's wheel loads, or when we use it, for example, in platform framing where we have a column underneath it, there's a major and a minor axis. And we have to consider both. And there's tests that we have established for CLT. As you can see here, this single piston puts 2-point loads in a two span to create and simulate a column load underneath, like you have here. The difference between the left and the right, one has a glulam horizontal element and a column, one does not. And so in this particular case, the column is point loading panels, and there's a major and minor axis issue to deal with in the design of it. Over here, we have just a major axis to deal with. And so some of the tricks of the trade are ledgering, for example, to create this ability to have post and platform framing, as you can see here, used in this building. And when we look at the design values, where did they come from? Well, this is CLT. These are actual values from our test lab just the last few days. CLT, transverse to grain shear in solid sawn lambs. These are ultimate values, and you can see from these values in PSI where you get the design numbers of 1 or 2 MPa in LSD versus ASD. This is mass timber rolling shear. This is veneer, and you can see here the same thing in this transverse, what we call weak or minor axis. A little bit better, but as you can see here at the bottom, they're still very weak in this direction. Why? Because if I have a veneer or I have a solid sawn CLT, when I put a shear line through here, in this veneer form, most veneers are rotary cut, and you have them with a knife and the log turning, it creates veneers, and there's little knife checks that come in here. And this coupled with that knife check, coupled with the loss of lignin strength, means that they're like a line of barrels. And when you put a roll stress on it, a shear stress, they all roll. That's where the term rolling shear came from. And plywood has got weak rolling shear. And so does veneers mass timber when it's got this cross banding. That's where you get the minor axis issue from, that cross banding that gives it dimensional stability, but creates a fault line in the shear. Versus this shearing action on the lower right and a solid sawn element, you can see it here. A different way it happens, but still happens in transverse. So when you take this platform framing and you have a column underneath it where major and minor axis become a problem with point shear, the way we deal with this, of course, is some of the unique ways that don't involve doweling is to use different composites of fiber that allow us to create an area where we transition by the biggest shear with the use of shear plywood and glulam facings, as you can see here, that allow us to then go on top of a column with what looks to be a platform and reduce the effective shear in the element and get ourselves down the road with a much more effective span and size of CLT panel, which of course it's all about size. If this size is governed by one individual area in terms of its minor axis, if we can overcome that problem, we'll make a much more economical design, as you can see here. If anybody would like a wood construction systems, this is a book I wrote with Greg Nolan for Australia and Southeast Asia. It's on wood solutions. And in this wood solutions, we go through case studies of different buildings. I can't imagine 20 years ago, if anybody was talking to me about putting a swimming pool on the 16th floor of an all timber building, I'd have laughed at them. But today, this is where the industry is going. And as I wrap up my session today, I want to talk just about fire, which is another area that's important for us. As we look for them 1 hour fire rating or 2 hour fire rating or 4, the taller in the building we go, the better our fire rating's got to be, because people have to get a chance to get out if there's a fire. And so wood has this great characteristic in that it chars. And when it chars, it shuts down further ignition. And so in combination with that, when we have stick built, we're used to using gyprock layers and creating fire barriers for our systems. And we have to do this in our fire systems today to get the resistance values we're looking for. Well, lots of times we want exposed columns, for example, or exposed horizontal elements. So part of what we've developed at the lab is through our fire testing, as you can see here in our big setup, is we've looked at fire resistance ratings and developed formula using high strength fiber. And how could this improve mass timber buildings? As you can see here, developing fire readings in minutes. And this is high strength fiber here. And so these test results have led us to some very interesting results. In addition to the fact that we have this great insulation capacity of wood, it also has the ability to give us some great upsides. And I just put this in here not to make a busy slide, but to show you when we do a fire resistance rating and we're trying to get the 1 hour rating, for example, we have beams exposed 3 sides or 4 sides. We have a way with high strength fiber to be able to get across the line with our ratings. And how do we do it? Well, when we increase the strength and moment capacity, for example, of an element by using high strength fiber, we get surplus capacity. And that surplus capacity leads to a higher FRR in minutes. And so if we have situations where we are not meeting our 1 hour rating and we want to get across the threshold, we can use reinforcement and get there, as you can see in this particular element, going from 49 to 62 minutes. In this next element here, I want to show is a column exposed 4 sides. We can take it from 54 minutes to 67 minutes. So not only do we get the increased capacity and get reduced size, but we get increased fire resistance rating, which is another big aspect for these tall timber buildings that we're getting into today. So this is another tool for engineers' tool bag, the ability to improve fire resistance ratings without going to extremely large sizes and making the structure less economical. And so with that, I bring to conclusion. I don't know where I am in my timelines. Dave will tell me. I hope that I have not gone over time. I should have set my clock up, but I didn't. And I'll be happy to take some questions.
Hey, you're right on time, Dan. Thanks. I always enjoy listening to your presentations. Thank you.
Thank you. You're welcome.
Yes. Yeah. So for everyone that's got any questions, please write in the Q&A section down below and I'll read them out to Dan. And there is one already here, Dan, and it's just a clarification on something. And they ask, so when using LVL, transverse shear could govern the design of the element, where rolling shear in the vertical glue lines could govern.
Yes, right. Typically, LVL is placed in our history. We've used LVL in a vertical form. And so horizontal shear doesn't really get us there. When we turn around and use it in plank form, lay it on its flat, for example, then horizontal shear can get us because of that minor axis side, because there's a cross-banding veneer in there that gives the stability. You have to make veneers stable. If you put all your veneers in one orientation, it's going to cup when it gets wet. So they put cross-banding veneers. And those cross-banding veneers is where we get that minor axis shear issue going. That's where we would get rolling shear, Dave.
Okay, perfect. And I'll just make a note too, those that are looking for the continuing education certificates for this session, it's just been posted into the chat box. So you just need to click the link there and download the certificate.
Yeah, they're asking about courses, Dave. You can direct them. You can direct them to Vicki Johnson, our registrar, if they're interested in our courses or some of the joint courses that we put on with you folks. And the next question was, has there been any economic impact analysis on buildings with wood versus foreign made steel? I mean, it's, you know, we, in the buildings and bridges, this is something I'm pretty passionate about. We hear this discussion today about what we call carbon neutral. And this is concrete and steel lobby talk, because they're gonna struggle to get to neutral. Timber is negative. I always talk about this. Carbon is negative. If you look at bridges and buildings that we've designed, we've done an analysis on, they're carbon negative, and that's where we need to get to today. I'm passionate about it because as I think about this, governments are considering carbon taxes, for example, and leveling different types of laws that will allow us to reduce the CO2 in the atmosphere by having these carbon tax. It makes no sense to me at all that, for example, with bridges, they would not allow a timber bid. If you go across to Canada today, you drive all the way from one end of the country to the other in Trans-Canada, you don't drive under one timber bridge. Yet we want to be carbon friendly, and nowhere do they, in these Trans-Canada, do they let you have a timber option in the bid. They only have steel and concrete. See, we have some tremendous hurdles to overcome, and we are overcoming them today by showing people that there's a better way forward. And that's an important factor for us. Another one there you can answer, Dave, is how is timber sourced and regulated, and do the regulations differ in the US and Canada?
I'm just replying to some of these questions right now.
And one of them is saying, do you see CLT manufacturing come in the Maritimes? I say yes. We're working with people right now that will be moving towards CLT and GLB manufacturing in the Maritimes as part of our code work over on the IAS side. We're looking forward to seeing manufacturing in the Maritimes in the next few years, particularly in glulam for bridges, for example, as we see manufacturing of timber, sustainable, carbon-friendly products, kind of migrate into each of the provinces. Just like a precast concrete girder manufacturer, we will have a manufacturing of pre-machined, post-assembled, post-treated glulam and mass timber bridges and buildings. Okay. And the other question is creep an issue with CLT panels like other materials? And the answer is yes. I mean, if you stay within your design values, then creep isn't an issue. Because in our design values, we have already put a factor, what we call an in-service factor, between the lower exclusion limit of our design, of our test set that was used as a basis to develop our design values. And in there's typically 2.1, a composite factor. That's 1.3 safety and 1.6 duration of load. So if your engineers are living within their design parameters, there's already been an accommodation for duration of load. And then we take what we call a CD factors, that's our durational load factors. And if we happen to have high percentages of our load dead, for example, library floors, then the design values are factored down to give us even more security against creep. So part of a design strategy is to understand what portions of our total load are dead and what portions are live, coming off and on. And so that's how we deal with that. You see major benefits to manufacturing CLT with EWP products like LVL, LS, and PSL. I do. It's another way forward for us in terms of further refining, because what do the engineer wood products do? In the 50s, when glulam started, 1952, when glulam beams started, what did we do? We said, okay, guys, we're going to take solid sawn timber elements, and we want to have a way to use some of the low grade and position the high grade. So what we did is we focused the high grade in high stress zones and put the low grade in low stress zones. And we made up a glulam beam, which was a composite of different grades of wood. And we said, okay, we're going to distribute localized defects and kind of reduce the risk of failure, and we get higher design capacities out of glulam beam, GLB. Then come engineered woods like LVL and Paralam and the other composite boards, and they did the same thing, only in a much more refined way. They made smaller pieces of wood and distributed them and put more binder glues in and increased capacities again. And so we've been constantly moving forward in the last 5 decades with the whole business of refining, reman, adhesives, and bringing wood fiber to bear in different ways to match the applied loads. And this is the refinement of wood that's gone on as we move forward in the last few decades. And the next one, there are CLT panels cambered to account for dead load. Typically, we don't have cambered CLT panels. They're flat panels, and we don't have them cambered like glulam beams. Glulam beams can be cambered. If you've been following my LinkedIn post, I just posted a pre-manufactured bridge that's sitting in a plant. And that bridge is cambered lengthwise and it's cambered widthwise, something you just wouldn't do in steel, that we could do with timber to give it great characteristics for asphalting, for loading and so on, give it that kind of great resistance to load. And so you camber glulam beams. Panels generally are refined to things that are going on in a flat zone. You know, they're horizontally flat, and you wouldn't want to camber the floor in a high rise, for example. You would want to camber the deck in a bridge, kind of a different way of looking at things. Not that you couldn't, but that's not how they're made. The next question is, how does salt aid in preservation? I showed you a picture of decay causing colony and how the hyphae grow from a spore when the moisture gets to 24% or higher. And that foot at the end of the hyphae secretes an enzyme. That enzyme is acidic, and that acidic enzyme breaks the wood down and makes it edible for the colony. What salt does is neutralize the pH wave, that acidic pH wave. And so interestingly enough, timber bridges and buildings that are going to be in salt environments are actually have more protection against decay and mold. The salt actually enhances their capacity to resist rot. That's why they're such a great combination for saltwater pools. For example, chlorine pools, fish hatcheries, that are in salt water. It's the right choice. And we've been building swimming pools out of wood over steel for decades, and building potash terminals with salt, and building coal terminals with SO2 problems, because wood has this great natural durability to different environments. What can designers and stakeholders do today to increase wood use in Atlantic Canada? I think that's, there's several ways, but some of the key ones. Look, educators have to produce more engineering students that know what they're doing with wood. We need more programs and teaching. 2, governments need to put their money where their mouth is. If they're saying they're carbon friendly and they want to be carbon friendly, why in tarnation are they closing all of their bridge tenders to timber? Why in tarnation are they still building precast and steel buildings and running out timber? Because of fire? These are lobby issues. They're not true issues. Timber has its rightful place as a competitor equal or better than other materials. It's been relegated to the bottom floor for decades. It needs to be brought back up, and that's what's going on right now. And the Maritimes, people in the Maritimes need to lobby their governments. Why are we doing this? On one hand, you say we want to be carbon friendly. You can't even buy a plastic straw in most parts of North America to suck up your Coke, but yet the government won't let you have a timber bridge in the tender. It's ridiculous. On one hand, we say we're carbon friendly, we're moving to carbon friendly, and we won't let them build a timber bridge. It's ridiculous. So, how do I see the future of automation and manufacturing, pros and cons? I feel like we're going to automated manufacturing. We're going to pre-machine, pre-assemble, letter and number like Lego, send it to building sites, all lettered and number, and people are going to put it together like Legos. That's where we're headed. It's the on-site work that has the risk, that takes the time. And if we can minimize that risk and time, it's going to be where we're going. While building a 10-story building, rain is likely. Does this pose an issue for CLT and glulam? It doesn't pose significant issue for glulam. It does if a flat surface CLT picks up water and lays with water on it. And I speak to this all the time for design engineers. When you're designing a building, it's not just about the bending stress and the stiffness and the shear, guys. There's a lot more to this game than that. What we want to have is engineers that understand the dynamics of wood's hygroscopic nature. It breathes in and out water, and when it does, it shrinks and expands. And when it shrinks and expands, it does funky things. And so even if I didn't have CLT panel DLAM, if it swelled up a half an inch, what's happening to all my fasteners in the rest of the building? So engineers have to understand wood, and this is why we need these training programs.